Well, we made it through the first video okay, and if you haven't, you need to stop immediately and go back and watch the first video of the summer, talking about instantaneous and average rates of change. Um, we're going to kind of dive in to look at limits, mainly just limits, not so much the rates of change. One thing you need to realize, and I put a star by it, the slope of a position time graph tells you the velocity of the object, or if you want a less complicated word, the speed of the object. To find the average speed using a slope equation, we learned last time that if you're on an interval from A to B, you would just find the y value at B minus the y value at A over B minus A. Again, that was the slope of a secant line, which was a way to find average speed. These are both the same thing, and they're found by just plugging into that. Again, if you haven't seen the first video, you need to go back and watch that. When we talked about how to find the instantaneous speed using the slope equation and a small time h, we didn't really go into detail with the small time h. We just said at some time x equals c, or x equals a, I think is what we actually said, we would use the slope of the tangent line would be equal to the instantaneous rate of change, which was always the y value at some point a plus 0.001 minus the y value at a all over a plus 0.001 minus a, which we knew all that just makes 0.001. That's why it's really important when you have a big strung out decimal here to keep all of it. Later we'll find out at some small time h how to deal with that. And basically you're going to take the limit of the function as h approaches 0. In this case, we had the h was 0.001. With algebra, that's as close as we can get to that original point A because we round everything to 3 decimal places. But using calculus, we'll be able to eventually find a limit as h becomes 0, not as the h is a 0.001. These 2 points are 0.001 units away from each other, where we can eventually find the limit as h approaches 0, or they're just infinitely close. They're basically the same point. And to really fully understand that, this will make a lot more sense when we're done with this lesson and you actually know how to find some limits. For now, you don't really know what a limit is. So limits can be defined a lot of ways. They describe the outputs of a function, or how the outputs of a function behave as the inputs of the function approach some particular value. We all know that the outputs are the y values. You know, some people replace this with the word y values. As the inputs approach a special number, and some people call those the x values. Okay? They're always written in this form: the limit of some function as x approaches c, where c is a number. You'll see several examples as we go through our work. Limits can be found several ways. One is through charts. It's a numerical way to find them. It's kind of mind-numbing. It's very simple, but it's just time-consuming. And although it always works, it's not going to be your preferred method because it's time-consuming. If you have a graph, you can find the limits usually pretty easy. If you have an equation, you can plug it in. And sometimes it will give you the limit. Sometimes it doesn't. The problem when you plug things in is that on occasion you might get what is called an indeterminate form. If you get 0 over 0, it's an indeterminate form. You learned long ago that 0 divided by some number, for example, 0 divided by 5 is 0. You also learned that any number divided by 0 is always undefined. You've also learned throughout your life that 7 divided by 7 is 1. 5 divided by 5 is 1. Any number divided by itself is 1. So according to this rule, you would think 0 over 0 is 1. According to this rule, you would think 0 divided by 0 would be 0. According to this rule, you would think 0 divided by 0 is undefined. If something is inappropriate, it's not appropriate. If something is an indeterminate form, it can't be determined. That is the way it is. They can be simplified, and quite honestly, 0 over 0 could be any number in the world. There are times when it will be undefined or not possible. There'll be times when it's 0. There'll be times when it's 1. There'll be times when it's 3 or 13 or 197 or negative 2 over 14. Well, that wouldn't use negative 2 over 14 because it would reduce to negative 1/7. But it can be a fraction, it can be a whole number, it can be positive, it can be negative, it can be big, it can be small, it can be 0, it can be undefined. 0 over 0 can be anything. And although most things can be done with charts, graphs, and plugging them in, we're going to spend a lot of time on things that have an indeterminate form, because that rare situation is where most of the work comes from. So on your homework, you're going to have a lot of 0 over 0 stuff. You're going to have also some easier stuff, but you're going to have a lot of 0 over 0 stuff. I always think that they talk about describing how the outputs or the y values of a function behave as the inputs or the x values approach a particular value. I always think of a limit as an expected y value. And you'll understand what I mean by that in a little bit. But just remember that. A limit is an expected y value. It's not always the y value. Sometimes it is. Sometimes it's not. When you plug it in, you get a y value. Sometimes that's the limit. Sometimes it's not. It's the expected y value. Let's look at page 2. With the charts, you can see these things. Basically, you plug in each x and get a y value. Very mind-numbing. You could go through, I don't know if you guys remember the whole, if we want to plug in the first one, there's several ways you can do it. You could take 1.9 stored as x, and then you could write x squared plus 2. You get 5.61. Write that down, so on and so forth. It's time consuming. And on the next page, you can see where I've already plugged them in. I don't care. I mean, here you can see every single one of them is blank. Okay. On this one, you can see that I've plugged them all in to save time. I don't care if you store them and write the equation again. Sometimes that's awkward. For example, this, you don't want to write that equation with all of those parentheses. Remember, you got to do parentheses around the whole top divided by the whole bottom. It gets awkward. So what I'm trying to remind you, hopefully you listen, hopefully you watch the video, is when you go, I typed all these equations in once. If you type in the first one, x squared plus 2, and notice these are not highlighted, so they're not turned on, so they will not show up. Okay, this is because I'm too lazy to retype them. If you would go to the table setup, let's start the table at 1.9, and we'll count by 0.1s. And then if you go to the table, notice at 1.9 it's 5.61. I could fill that in. I could also go down and fill the 2.1 in. At 2.1, we have 6.41. Okay, then when I went to 1.99s, I got to change my window. I'm going to start at 1.99, and I'm going to count by 0.01s. And then I can go to my table. 1.99, I have 6.960, it looks like. Excuse me, 5.960. You got to round to 1 decimal place, or to 3 decimal places. Excuse me. Also, if you want 2.001, you could scroll down here 2.0. Excuse me, I said that wrong. 2.01 is 6.040. I'm only doing 3 decimal places. All of AP Calculus, they use 3 decimal places or they use exact values. They never round to more or less than 3 places unless they tell you to. When you want the other ones, the 1.99 and the 2.01, you can go and type in 1.999 and go to the table of count by 0.001s. And when you go to the table, it'll give you 1.999 is 5.960. 6.996, which is what I put down. 2.001 is 6.004, which is what I put down. If you don't like this, remember you could always store stuff. Like you could take and you could type in 1.999 stored as x, but then you got to write in the whole equation, x squared plus 2, and you get 5.996. That's okay on this one, but when you get to these, that's really awkward because you have tons of parentheses and you got to retype it all. Whereas if you just plug it in down here where we graph, you can go to the table. As you can see, I've typed in all these equations before. I deleted that one earlier, sorry, but I had it in there and filled them all in, except the last one. We'll get to it in a minute. The idea is when you have a chart, if you're wanting the limit of this function as x approaches 2, that is the equation y equals x squared plus 2. You could look at that curve, you know it's a smiley face up, and you could look when x is 2 and what the y value is. But you can tell when x is 1.9, this is your y value. As is 2.1, this is your y value. As you get closer to 2, 2 is right here, isn't it? As you're coming in on the left side, numbers are getting bigger. As you're coming in on the right side, numbers are getting smaller. What number does it appear it's going to reach between these two numbers? Between these two y values, it appears like it is going to reach a 6. If you notice, if you plugged it in, 2 squared plus 2 is 6. So whether I plug it in or whether I do the chart, I get the same answer. Obviously, plugging it in is much quicker than me filling out this chart. Now, will plugging it in always work? I told you on the first page, plugging it in only works sometimes. Okay? Charts always work. They're time consuming, and because of that we don't use them much, but plugging in always works. Graphs, and we'll do graphs in a few minutes. Okay? When you look at this, this next problem, quite the complicated fraction. As you plug in a 4, you would get 4/5 minus 4/5, which is 0. If you plug a 4 in the bottom, you would get 0. That's the indeterminate form. Can't do it. Plugging in only works sometimes when you get real answers. If you get an indeterminate form, you can't do it. You'd have to simplify it. We'll work some problems like these later, but for now, simplifying would be getting a common denominator. And then as you work through the problem, you'd have fractions divided by a non-fraction. You can make them both fractions, flip and multiply, yada, yada, yada. Things will cancel. Life will be great. We'll get into that later. That's a little more complicated. For now, you could just fill out the chart. And you can tell if you're going to 4, 4 would be right here. Now, on this case, you would notice that way before, you would get the 3.999 and 4.001. Okay? You don't always know that. That's why they typically do 1 decimal, 2 decimals, 3 decimals on each side of it. They go from 4.1 to 4.01 to 4.001. And that same amount on the other side. So 3.9, 3.99, 3.999. And they work their way in. That way you can notice a pattern. Well, you can tell this pattern between those two numbers will be exactly 0.040. So, yeah, in this case, 0 divided by 0 isn't 0. It's not undefined. It's not 1. In this case, 0 divided by 0 is 0.040. We will have some that involve trig. But if you're using your calculators to get these values, you got to be in radian mode. Okay? There's no degree sign. It's x approaching 0 radians. And you can tell as you do that, 0 radians would be right here. And as you're coming in from the left and coming in from the right, they approach the exact same number. And what is that number? Well, it's going to be between 1 and 1, which is 1. Now, in this case, had you plugged it in, notice you would have gotten a 0 on the bottom. And if you plug it in the top, the sign of 0, well, the sign of 0 is 0. It's the y value at 0 on the unit circle over 0, which is an indeterminate form. you can't really simplify that. That's kind of a really important equation, okay? If you're doing the 12 basic functions from pre-calc, this should probably be the 13th basic function. It is used quite a bit. You just kind of got to know what sine of x over x looks like. And I'm typing it in, and I'm going to look at the window. Let's go from negative 2 pi to 2 pi. And we'll count by pi over 2s or something silly. I don't really care. The y min will do negative 5 and 5. I think you'll get the idea. You can see it's like a little bell curve. It crosses at 0, 1. As you go to the right, it's got a horizontal asymptote at 0, and as you go to the left, it becomes 0. Okay? If you wanted to zoom out and look at it, you could. It's going to become 0 as you go out to infinity on the right. It's going to become 0 as you go to infinity on the left. Whether it's going up and down above it or not, it looks like it is, but it's still going to be 0 as you get away from the x-axis. As you get close to x-axis, or as x approaches 0, it looks like it's going to have a y value of 1. If you go to the table, you could kind of look at this. And when you look, at 0 you get an error. But you can tell on each side of 0, you're really close to 1. When you go out here very far, you're getting infinitely closer. Those y values keep getting lower and lower and lower. Okay, if I want to type in like 55, I thought it would let me type in just 55, but it won't. I mean, I can just scroll down forever. You can tell it's getting close to 0. It goes one side, it's going negative, and then it'll come back positive in a minute. And then it'll go negative again. But, I mean, they're getting close to 0. Okay? So in that case, I mean, you got to kind of look at the graph when you got 0 over 0. With this cosine of x minus 1 over x, same thing. As you come in on both sides, you can tell it's between 0.0005 and negative 0.0005, which means as you approach 0, which would be between these two numbers, you're going to get a number between those two, which if you find the average of those two, you get a 0. Had you plugged it in, you would have gotten 1 minus 1, which is 0, and 0 on the bottom, and we all know 0 over 0 is an indeterminate form. That's why the chart would work. If it's an indeterminate form, the chart will work. Not very time efficient, but it works. Okay? For some reason, number 3 at the bottom seems like the most impossible thing in the world for kids. If the y value is a 7, are there any variables here? So, can I plug a 0 in for an x? No. So what am I going to get? If I can't plug anything in, my answer is going to be 7. If you look at these numbers, I can't plug them into a formula. Or if I do, there's nothing there. It's just going to be a 7 as my answer. If you think of this is the line y equals 7. Do you remember that's a horizontal line at 7? Well, when I come in to 0, whether I come in on the right side of 0 or the left side of 0, my y value is a 7 no matter what. It's always 7s. It doesn't matter which one of these I plug in. There's nowhere to plug it in. Your answer is going to be a 7 everywhere. So the limit as you go to 0 is going to be 7. Every time. There's no variables. It's just whatever number's there. Okay? Don't make it harder than it is. Let's look at some graphs. I have these out of order. Did we start on number 9? That's kind of weird, but I guess we started on number 9. Well, by the way, I'm just pointing out, when you looked at page 1, you remember the basic limit is written limit as a function as x approaches a number c. Well, here's my function. Notice that's the line y equals 4 minus x. It crossed at 4, had a slope of negative 1. We're looking when x approaches 3. Well, if you come in from the left side, as you're coming in this way, the y values start at 2 and they're getting smaller. As you get close to 3, it's not always the y value at 3. You'll understand what I mean in a few minutes. As you get close to 3, the y value is getting close to 1. When you come in on the right side, my y values start down here at 0, and then they get a little bit bigger. And as you're getting really close to 3, the y values are getting really close to 1. If the left side approaches 1 and the right side approaches 1, then your actual limit is a 1. And notice in this case you could plug a 3 in and you would have gotten 1. On the next one, if we're looking when x approaches 1, well, here's 1. X approaches 1. As you come in on the left side, the y values are getting bigger. They're getting close to a 3, aren't they? As you come in from the right side, the y values are getting smaller. They're getting close to a 3. Well, if the left side gets close to 3 and the y value gets close to 3, then the actual limit would be a 3. Notice if you plug the 1 in, you would have gotten 1 squared plus 2, which is 1 plus 2, which is 3. You could have plugged it in. Remember, when you look at the charts, you're going to look on the left and on the right and see if they're coming up with the same number. If they're the same number, then that's your limit. If you're plugging things in, as long as you don't get 0 over 0, it's your answer. Okay? If you get a number, you're good. If you get 0 over 0, you have work to do. Okay? Now that work could be in the form of creating a chart, which although we'll have you do charts in this section, a month from now you're not going to be doing charts. You're just going to simplify it with algebra. Okay? Even really a week from now, you're not going to be doing charts. There'll be 1 on the quiz, but there's not going to be 10 on the quiz because they're the most awkward thing ever. I want you to remember you can do a chart, but most normal people don't do charts. They're just way too time consuming. Okay? Here, if we have a step function, this is a good one. If you approach a 2, when you plug 2 in, you get 0. And notice the y value at 2 is 0. But as you approach 2 from the left side, you're coming down through here. We're at 3, we're at 2.5, we're getting close. We're getting really close to 2. As you come in from the right side, you're at 1, you're at 1.5, you're at 1.8, 1.9, 1.99999. You're getting close to 2. Remember, a limit can be an expected y value. The actual y value is 0. When you plug it in, you get a 0. But if you're cruising in on the left side, you're getting close to a 2. When you're cruising in on the right side, you're getting close to a 2. The actual expected y value is a 2. If there's a hole in a graph, you have to look at the expected y value. I don't care where this dot is. That dot is insignificant. When you're coming in from this side, you're expecting a 2. When you're coming in from this side, you're expecting a 2. Therefore, the limit is 2. Okay? Number 12, when x approaches 1, the y value at 1 is a 1. That doesn't always matter. Don't think the limit is 1. You've got to look at the actual curve. Okay? You could plug in, doing the chart, you could plug in if you're looking when x is 1, you could look at, 1.1, 1.01, 1.001, which would all be plugged into the top equation. You could also plug in 0.9 and 0.99 and 0.999, which is all plugging in the top equation. You could compare your answers. But it's easier to look at the graph. As you come in on the right side, left side, I don't care which one we look at first. If you're coming in the right side, we're at 4, 3.5. We're getting down here. We're getting really close to a y value of 3. When you cruise in on the bottom, you're down here at 2. You're going up. You're like, 2.5, 2.6, 2.7, 2.8, 2.9, 2.999999. You're getting close to a 3, aren't you? The expected y value from both sides, the right side and the left side, is a 3. Therefore, your limit is 3. It is not the y value. The y value is whatever the dot is down here. It looks like a 1. The limit is the expected y value. Obviously, when it's a continuous function, When it's a continuous function, the y value and the expected y value are the same thing. When it's not continuous, and a hole is an example of when it's not continuous. Remember, vertical asymptotes are another example. Jumps are another example. Okay? When it's not continuous, you can't plug it in. You have to look at the expected y values, which could be done with a chart. It could also be done by looking at the graph as you come in each side. Okay? I told you sine of x over x is an important graph. X over x is 1. If one of these had an absolute value, whether the top does or the bottom, either one, these look the exact same when you graph them. Okay? These two functions look the same. If x is positive, that means you're on the right side of 0. If x is positive, the absolute value bars are insignificant, and you would just have a 1. So if you're on the right side of 1, it's just a 1. A horizontal line, y equals 1. If you're on the left side of 0, well, you would have a positive here because the absolute value, and you'd have a negative down here. Like if you plug in negative 9, you would have a 9 over a negative 9, which is a negative 1. If you plugged in a negative 5 for x, you would have a positive 5 over a negative 5, which is a negative 1. No matter what you plug in, they're going to cancel, but the top is positive, and if you're plugging in a negative x, it's a negative in the bottom, giving you a negative 1 as your answer. So you can tell it's just a horizontal line that jumps to another horizontal line every single time, no matter which way it's written. And of course, it's undefined at 0, because you can't divide by 0. Notice there's the holes at 0. There's nothing colored in. This is the same thing, but it's been moved right to the right 5. If you plugged a 5 in, you would have a 0 over a 0, which is an indeterminate form. If you look at the graph, and this isn't a bad graph to remember, it's just this one, the one that jumps, but it's jumping, instead of jumping at 0, it's jumping out here at 5. Because they cancel, you'll have a positive 1 on the right of 5 for numbers bigger than 5 that get plugged in. For numbers smaller than 5, you would get a negative on top and a negative on the, you get a positive on top and a negative on the bottom. So you get a negative 1. So as you can tell, as you're cruising in on the left side here, it looks like our y value is going to be a negative 1. As you're cruising in on the right side, our y value is a positive 1. Well, if one way I expect a positive 1 and one way I expect a negative 1, it's really hard to get an expected y value, because there's a big difference between 1 and negative 1. You can't just assume it's 0. Okay? You can tell the expected y value, well, there's a big gap right here. This is when the limit does not exist, because the right-sided limit and the left-sided limit are different. When you come in from the right, you expect one number. When you come in on the left, you expect another number. The limit does not exist. For example, up here, when I came in on the left, I expected a 2. When I came in on the right, I expected a 2. That's the same number, so my limit was 2. If my right and left sides cause me to expect different answers, then the limit doesn't exist. For example, we all know this has a vertical asymptote at 3, at x equals 3, and it did. Okay? If you plug a 3 in, you would get 1 over 0, which is undefined, so you can't plug it in. Okay? If you would look as you approach 3 from this side, do you see as you're getting close to a 3, here's 3, as you're getting close on the left side, it's going to negative infinity. As you're getting close on the right side, it's going up to positive infinity. Well, because those are different numbers, we're going to have to say the limit does not exist. You want to look at tangent. If you plugged in a pi over 2, that would be a sine of pi over 2 over a cosine of pi over 2. The sine at 90 degrees, or pi over 2, is a 1. The cosine is 0. That's undefined, right? If you look at the picture, at pi over 2, one side goes to infinity. The left side, the limit would be negative infinity. Well, they're not the same number, therefore the limit does not exist. Notice we didn't have an actual real number here. Okay? When you plug it in, if you get 0 over 0, you need to investigate further. If you get undefined, you need to investigate further. Usually, if it's undefined, the limit doesn't exist. Okay? In this case, it was 0 over 0, and it still did not exist because it jumped. If you want to look at the secant curve as x approaches 0, well, as you come in on the right side, it looks like this would be a 1. As you come in from the left side, it looks like it would be a 1. Because the right-sided limit is 1 and the left-sided limit is 1, the actual limit is 1. So just because you see a trig word, don't think it's going to be 0 or does not exist. It could actually be a real number. Okay? When you look at the next one, and this is a rare thing, but if you have a cosine of 1 over x, do you realize if you plugged a 0 in, you would get undefined? Well, what happens is you get infinitely close to 0, it just bounces back and forth. It never settles to a number, because when you think you're plugging something like 0.001 in, you could always plug in 0.0000001 or 0.000000001. You can always get closer to 0. And because the sine and cosine curves are periodic, if you would have cosine of 1 over x or sine of 1 over x, they're going to bounce back and forth. They're never going to give you, they're never going to approach a specific number. They're going to keep bouncing back and forth. So your limit will not exist. Okay? Your limit will not exist. When you look at the next one, if you look at the limit of sine of pi x as x approaches 1, well, when you look at the graph, as you come in on the left side, it looks like these y values are getting really close to this, which is 0. When you come in on the right side, it looks like they're getting really close to this spot right here, which is a 0. Because they approach 0 on the left and 0 on the right, the limit must be 0. Now, the reason I left some space, if you plug it in, you would get sine of pi times 1, which is pi. And we all know from knowing the unit circle, the sine at pi, which is right here, is 0. So you can plug it in. If you get a number, you're good. If you get something that's undefined, look at it and make sure it probably does not exist. If you get something like 0 over 0, you need to look, because it may not exist, like the one that jumped. And the absolute value of x over x, or x over absolute value of x, is the same thing if you're looking when x is 0, because that's what makes it 0 over 0. You could get one that's an actual number, like these. On these, when you plug them in, you got, that's not the paper we actually did it on, but on these, when you plug it in, you get 0 over 0, which was 0. Here you got 0 over 0, which was a 1. Up here you had 0 over 0, which was actually 0.040. That indeterminate form is going to be where you earn your money. We're getting kind of a lengthy video here, so I'm going to go ahead and stop, and we'll start here with the properties of limits on the next video.